In this video, we will be discussing the Inference Toolbox. This will help you for project number 4 and problem 9.41 from assignment number 11. If you haven't done so, download the document that says Inference Toolbox for confidence intervals, and it's this little outline, this state, plan, do, conclude outline. We'll be using that for this problem. Okay. The problem states that we have a sample of doctors in training, that is resident doctors, who are working a second job, moonlighting. It says 38 over 115 of these doctors have to work a second job due to debt. All right, so our sample proportion is 38 out of 115. 38 out of 115 doctors in this particular sample moonlighted, worked a second job to pay the bills. They're doctor residents. They're not quite full doctors yet. They're still in the last phase of their training. Okay. A part says construct and interpret a 95% confidence interval for the proportion of U.S. medical residents who work moonlighting jobs. So we're going to employ our inference toolbox. The first part is to state. In this section, we will state the following in context: that we are constructing a confidence interval, what the confidence level is, and the parameter we are estimating. And the parameter is either a proportion or a mean. Those are the two parameters that we've discussed. So for this particular problem, state we will construct a 95% confidence interval for the proportion, that's a percentage, of resident doctors, doctors in training, who moonlight, work a second job. All right. We have some sample. We're going to take that sample and shoot at the whole world of resident doctors, all of the resident doctors out there. Try to figure out roughly how many of those indeed have to have a second job. All right, that is my statement. I have stated my confidence level. I've stated that I'm constructing a confidence interval and that I'm dealing with proportion. That is not a mean, but a percentage of people. All right, next is plan. In the plan section, in this section, you will check the conditions of inference. They are, did our data come from a random sample? Remember, how we select the sample matters. We can contrive a sample that can say anything at all, but if we properly use randomization, then our sample should be representative of the population. 2, is it appropriate to use a normal approximation? Thus far, we've only studied normal approximations in our inference, so we want to check to see if it is appropriate. For means, we have this rule. If our sample is relatively large, greater than 25, we can invoke the central limit theorem. If it's less than 25, we're going to show a graph. But here we're looking for proportions. For proportions, we need to check the rule. N times, this should say p hat. N times p hat is greater than or equal to 10, and n times 1 minus p hat is greater than or equal to 10. This is the successes and failures in the sample. So, state. So number 1, we want to know, was it a random sample? Okay. Is it a random sample? Well, stated in the problem, yes it was. Stated in the problem. normal? That is, can we use a normal approximation? Well, since it's a proportion, we want to know, is n times p hat greater than or equal to 10? And separately, is n times the complement of that, 1 minus p hat, is that greater than or equal to 10? Well, for this one, our n, our sample size is 115. That's our sample size. That's n. Our p hat is 38 out of 115. Well, notice the 115 cancels with 115. That's a 38. And 38 is greater than or equal to 10. What we verified here is that our sample is pretty large. If we have a sample of size 115 and we have relative decent success of capturing whatever it is, then 115 is going to get it done. We will be able to use our normal approximation. Now we check the other half. It's n times 1 minus p hat. Well, this is our number of successes, 38, so the other half is the number of failures. I'll show it. It's going to simply be 115 minus 38. So 115. The rest, if we had 38 successes, then we'll have 77 fails. And by fails, I mean not what we're counting. Okay? 115 divided 115, that leaves 77. And that is indeed greater than or equal to 10 too. So we have satisfied our conditions. That is the plan. State, plan, now do. In our do section, we're going to construct the appropriate confidence interval. Well, our generic confidence interval is some estimate plus and minus some critical value times a standard deviation of a statistic. Standard deviation of a stat. Okay. This is our best guess from our sample. This is how far we're going to jump, how many jumps I should say, based on our confidence level. And this is how big those jumps are, the standard deviation. This entire factor here is called the margin of error. Margin of error. Okay, so for our particular problem, our estimate is our sample proportion, that's p hat. Our critical value is the z star, and we there are many z stars, but I'm going to look at a few that we will be interested in. All right, if our confidence level is 90%, the z star is approximately 1.645. This is the confidence level. Confidence level. This is the z star critical value. Okay, if it's 95%, which is our default, the critical value is 1.96. You see this is almost 2. 95% is 2 standard deviations. That's what that is. All right. For when we're dealing with a normal approximation. For 99%, it is approximately 2.58. And you notice as our confidence level increases, the z star increases. That makes sense. To be more confident, we need to go out further. Okay. Our standard deviation of our statistic for the proportions from our sampling distribution section said this. It's going to be the square root of p hat times 1 minus p hat divided by n. Okay. So for this particular problem, our p p hat was 38 over 115 plus or minus our z star is this number here, 1.96, times square root of p hat is, again, 38 over 115 times 77 over 115, all divided by 115. Okay, 38 over 115 is approximately, this is approximately 0.33. That is 33% of that sample. This entire factor over here is at roughly 0.044. So this is about 2 times 0.044, that's about 0.09. This is our confidence interval. This is 33% plus or minus 9%. Stated another way, I can look at 0.33 minus 0.09, that's 0.24. 0.33 plus 0.09, that is 0.42. This factor here is called our margin of error. That's our plus or minus, that's our give or take, okay? All right, lastly, we conclude. In the conclusion, we'll state the interval in context and interpret the meaning. Okay, so we're going to state our interval in context and interpret the meaning. We will say this: we are 95% confident the true proportion, the percentage of resident doctors who moonlight, work a second job, lies in the interval .24 to .42. What we're saying is we're 95% confident it's from 24% to 42% of the doctors have to have a second job. Okay, what does this interval mean? Well, it doesn't mean there's a 95% chance it's in there. The true number, we either caught it or didn't. It's either a 0% chance or a 100% chance. Essentially, this is an already flipped coin. Okay. Before you flip a coin, we'll say there's a 50% chance it can be heads. After you flip it, it's either heads or tails. That's what we have here. We have an already flipped coin, okay? But we can say about future ones, all right? This interval, okay, that is, in the long run, here's our frequentist probability interpretation. In the long of intervals constructed in this manner, we will capture the true mean, but for us it's proportion. That is, in the long run, 95% of intervals constructed in this manner will capture the true proportion, the true percentage. All right, this statement here says nothing about this particular interval we constructed. It's about our methodology. If we do this thing over and over, we expect 95% of them to be successful in capturing that unknown parameter. We don't know if this was one of the unlucky ones, so to speak. All right, you are going to use this format in project number 4 and for this problem 9.41.